Hi, it's Mr. Andersen, and this is AP Physics Essentials video 134. It's on the wave function. Wave function can be used to calculate the probability of finding matter in one area or another area. And so let's start with a different kind of a wave, crime wave. This is a map of Washington, D.C., and it shows where murders occurred from 2004 to 2006. So you can see there are certain areas where we had more murders than other areas. Now, does it tell me where the next murder would occur? No, it just shows me where there's a higher probability of it occurring. And we use the same thing to describe where matter is. So for example, electrons, this doesn't show me where the electrons are, it just shows me where there's more probability of finding those electrons. And so matter can be treated as a particle or a wave. As we get smaller and smaller and smaller, remember, we have to shift to the wave model. Before we get to that, let's think of particles. A particle in a box could be here or here or here. But if it's here, it's not going to be anywhere else in the box. But waves are different. We have to use a really complex wave function to calculate the probability of finding that matter in one area or another. So if this is our box and we're using the wave model, we take the absolute value of the wave function and we get something like this. This is going to show us the probability of finding the location of matter in that one area. And so in AP Physics, you have to be able to read a wave equation or a wave rather function like this and figure out where's probability more likely. So before we get to that, let's start with a double slit experiment. Imagine we have a wall right here and it has two openings in it, or two slits, and we're going to fire paintballs through it. So as we shoot them through it, they'll hit on the screen, and if we look at where they're distributed on the screen, it would be somewhere like this. That's because paintballs are like particles. Now, if we were to cover up one of those, then we would only have the particles on the bottom side, and likewise, if we cover the bottom, only on the top side. But that's how particles behave. If we're doing waves, it's different. Let's say these are water waves and we're able to measure where their amplitude is on the other side. So they're going to interfere with themselves, and what we'll get on the other side are areas where we get huge waves and areas where they cancel each other out. Waves are different than particles. Now let me kind of ask this question to you. What would happen if we used electrons instead of paintballs? Well, you might think they look just like paintballs, so we're going to get that same distribution. What's interesting is that you get interference, and so you get this wave property. And that indicates that electrons are acting like waves, and this makes sense. They're interfering with each other. If we look at a screen in the back and let those electrons fire through, they'll build up, and you'll get interference that looks like that. Now, that's a little crazy if you think about it, because what they're doing is they're interfering. These are the first electrons, the next electrons, the next electrons. Even though they're going through one at a time, they're actually interfering with electrons in the future or in the past. That's kind of crazy. It gets crazier than that. If you look at one of these slits, and so if you look here to see, is the electron coming through this one or that one, something puzzling happens. And what happens is they go back to acting like particles again. And so the whole wave function is confounding to scientists, and we can't measure it. If we actually look, what happens? They quit acting like waves. And so how do you read a wave function? Because that's what you have to do in this class. Well, it'll look something like this. If this is a wave function of a particle, you could be asked, are we more likely to find the particle at x1 or x2? And the answer is really simple. We're going to find it more likely at x2. Why is that? Because we have a greater amplitude of the wave function here than we do over here. If we were to try this problem, so if we have two wave function, A and B, that represent two particles moving in the direction of x, would we more likely find it at x0 on the left side, here, or here? So what's the right answer? How do you read this wave function? Well, the right answer is going to be here at B, but why? Again, it goes back to amplitude. So it's only going to be the amplitude. And so don't worry about it's so compressed here. That doesn't tell you anything. What you always want to do when you're looking at the wave function, find the highest amplitude. That's going to be the highest probability. And so did you learn to use graphical wave function to figure out qualitatively where that matter or that matter wave is going to be? I hope so, and I hope that was helpful.